My name is Müller, and this is Coroutines C++ versus Rust. In this talk, I obviously can't give you a full tutorial into coroutines in either C++ or Rust. Both are very complex topics with lots of nuance and small details. Instead, I will just compare the general approaches, contrast them, and give you like an overview. You can then jump in and learn more if you're interested. Okay, I will assume that you know C++. I think this is mostly a C++ conference, so that is fine. I will not assume that you know Rust. So if there is any syntactical Rust syntax, I will point them out as necessary. If you have any questions during the talk, which might be the case because it's a bit of a complicated problem, feel free to ask them and I'll answer them. So let's begin. Usually when coroutines are introduced, they are motivated by like network sockets and multi-threading and so on. I've decided against that here. So let's just start with a very simple example. So we have the AI of some guard in an RPG or something, and we just wanted to move between 2 points. So it's on a patrol, it just wants to move back and forth between 2 points. So in 2D, we can render it in ASCII. So the guard is this hashtag, and then it moves to the right, and then it reaches the endpoint, and then turns around and goes back. And we want to implement that. It's very straightforward. We simply write a function, we write a loop, we set the position to the start position, we set the direction to positive, and then we advance it. And when we reach the end, we have a turnaround. Now, this works fine, but for timing reasons, we have to sleep here. Otherwise, right, this would just advance on and on and on and go really way too fast. So this sleep call here to just stop the time isn't ideal because it blocks the entire thread. Right? If we have 2 guards, we have 2 sleeps, so now the time is half as quickly. So we actually need multi-threading. So we start the patrol function on a separate thread, update the position, and then have the guard move back and forth. Yeah. While this works, we need to keep multi-threading in account and synchronization. It simply doesn't scale. If we have multiple guards, we need multiple threads. So yeah, this approach doesn't scale to more than like a couple of guards at most. So nobody's actually going to write it like I've shown you. Instead, we have some sort of state machine. So here I've written it very explicitly. So we have the state, which is the position variable that we're updating the current direction and start and end. And then we have a function init that initializes the state and sets it to move the guard moving right. And then we have an update function that simply does the calculation of the previous loop. So we advance but one step only. So we advance the state by the direction. If we reach the end, we have a turnaround. Now our main loop looks slightly different, and we don't have any threads at all. So we call a patrol init to get the initial state, and then in an infinite loop we repeatedly update it after sleeping. And this now scales easily because if you have 2 guards, we simply call patrol init twice, get 2 states, call update twice. Right? Now more multi-threading issues, it works, but the downside is, of course, the patrol update function is a lot less readable than the previous loop, right? We are just doing a single thing inside the loop and don't have it as explicitly anymore. Coroutines can help this because coroutines are functions that can be suspended and resumed at a later point. So where we have a regular function, we can call it, then the function executes, potentially calls other functions, but eventually it finishes and returns back to the caller. A coroutine is a function that can be called, and then it starts executing, and then at some point the coroutine decides, okay, I'm going to be suspended now, which means it transfers control back to the caller. It's then suspended and then later resumed from there. And the idea is to have the compiler generate the state machine for you and combine the best of both worlds. We have the easy readable code from the multi-threading examples, but internally have generated the state machine. So this is the patrol function implemented using coroutines. It looks exactly the same. I'm using some sort of pseudocode here, so some pseudo syntax. It looks exactly the same as the multi-threading example, but instead of sleeping, we're suspending. So I'm using this pseudo continue return here to mean suspend the current coroutine. Then the main loop, this looks exactly the same as the code with the state machine. So we are calling the patrol function. This gives us some sort of handle, which was the state in the state machine example. And then we're doing a sleep once and resume execution of the coroutine. So this is visualized in a diagram here. We have a main function, which calls the patrol coroutine, which is then activated and starts executing. At some point, it's suspended, returns control back to main, it's later resumed again, and can be suspended and so on. So let's see how coroutines are actually implemented in C++ and Rust. For that, we will first define some necessary terminology. So let's jump into it. So a coroutine. A coroutine is a function that can be suspended and later resumed. And here I'm limiting the term to mean the programmer written version of a suspended function. So a coroutine is the thing the programmer writes that is suspendable. Questions we need to look at is how do I indicate that a function is a coroutine? What happens when you actually call a coroutine, right? Does it immediately start executing, or is it suspended initially? What is returned when you call a coroutine? So we need to get some sort of handle back. What handle is that? CPU can't execute a coroutine directly, so the compiler has to transform it and lower it into something that can be executed in a CPU. This is the coroutine state machine. It's the compiler-generated implementation of a suspendable function. It supports 3 operations. The programmer can suspend the coroutine, so it can suspend the current execution and later resume it. It can suspend the coroutine while waiting for something, and when that something is ready, the coroutine is resumed automatically, and the programmer can exit the coroutine. Open questions here are, what is the initial state of the coroutine? So when you call the coroutine, does it start as suspended or not? Also, what is the final state? So when you're done with the coroutine, what happens then? And how much control do we have over this compiler-generated state machine, right? Can you tweak it a bit? Can you customize it? And so on. The coroutine handle is the interface thing that is used to control the coroutine. So the programmer can query whether the coroutine is done. The programmer can resume execution of the coroutine if it isn't done and it is currently suspended. And potentially the programmer can also preemptively destroy the coroutine. So when the programmer doesn't want to have the coroutine running anymore, it can destroy the coroutine. Questions here are, is there a single handle for all coroutines or the different types? And can you also implement the handle for something that isn't a coroutine? So when you write your own state machine, can you use the coroutine handle for that as well? Or do you need to use a coroutine there? An awaitable is an entity that can be awaited inside the coroutine. And the questions here are, what can be awaited, right? What are awaitables? And how do you write your own, right? So an awaitable is something you can await it in a coroutine. This will then suspend the coroutine and have it resumed later. The resumer is what I call the entity that actually resumes the coroutine when it can make progress. So when a coroutine awaits something, it is suspended and then it's later resumed. And who is responsible for resuming it? Is it the original call of the coroutine? Is it the awaitable, which sort of resumed the coroutine itself, or so on? It should resume it when the coroutine can make progress. But how does it know when the coroutine can make progress, right? How is that informed? Where does the information flow here? So we will now go over those questions and look at how they're answered in C++ and Rust. So let's start with C++. I believe the model in C++ for coroutines is a bit more low level than the one in Rust, and it also provides more opportunities to look at various details. So it's a nice fit to start with C++. We will later then look at Rust and see how they did it. So in C++, a coroutine is a function that uses co-await or co-return. It can also use co-yield, but I'm ignoring co-yield because Rust doesn't have it. The compiler then generates a state machine from that coroutine, and this can be controlled by something called a promise type, which is a user-defined type. And it can, the state machine is controlled by user-defined type, and it can be advanced using the coroutine handle, which is the standard Laravel type std coroutine handle. So this is a very basic coroutine. My coroutine, it simply prints something and then returns 42. As you can see, whether or not something is a coroutine is entirely an implementation detail, right? Just looking at the signature, you can't tell that this is a coroutine. That's the regular function that returns this type task int. You also see that the specified return type here, task int, which is also the type you get when you call my coroutine, doesn't match the type returned here. So we're returning an int, but the function return type isn't task int. So there's some sort of mismatch and we're returning a fancy type instead. The promise is used to control the coroutine, and it has the following required functions. So the function get return object. This constructs the type that is actually returned by the coroutine function. So in our case, this would be responsible for returning the task int object that is returned by the coroutine. Then we're having initial suspend and final suspend. They control the state machine and control whether the coroutine is initially suspended. So when you call it, does it start executing or is it suspended? And what happens when you reach the co-return statement? Is the coroutine then suspended or does it clean up itself and exit the coroutine? Then it can be the case that an exception escapes the coroutine, which you want to control. So this function unhandled exception is called, and then you can use it to like translate the exception or do something. I'm going to ignore it for the remainder of this talk. So just pretend I've implemented it appropriately. And finally, when we want to use co-return inside the coroutine, we need to write return value. This is called by co-return value. We can get the value, and then we're responsible for storing something. The coroutine handle is used to control the coroutine. It's a standard library type. It has the functions I've described before. So we can query that the coroutine is done. We can resume a coroutine that is currently suspended, or we can destroy it. It's templarized on the promise, so we can construct the coroutine handle from a promise object when we have one, and we can also get the promise back. But there's also a type erased version if the promise is void. Then this can be used for arbitrary promises, but we don't get access to the promise back, obviously. Coroutine handle is essentially the equivalent of a var pointer for a coroutine. So it's a non-owning thing, copyable pointer to a coroutine. So for the purposes of this talk, I've written the little class unique coroutine, unique coro, which is essentially the unique pointer equivalent of a coroutine handle. So it is also templatized on the promise, and it's just a move-only type. It's destructible, automatically call destroy, and so on. So it's the unique pointer version of a coroutine handle. And that way you don't need to worry about any cleanup in all the context objects. So with that, we can implement the task. Because in C++, the coroutine is controlled by its return type. In our case, this is task. And this happens by defining the promise type. There's also a way to do it via traits. I'm ignoring that here. So the promise type is the promise of the coroutine that is being used. This is then used to actually implement the coroutine, as we'll see. And then the user interface has two functions, resume, which resumes the coroutine, and then we can get a result if we have one. Otherwise, it's empty. Internally, it simply owns the coroutine and is responsible for its destruction. So all the interesting stuff happens inside the promise type. So we need to implement getReturnObject to construct the task. This is straightforward. We simply are inside the promise, so we can use it to get a handle and return that into the task. When we want to call coreturn, we need to store that value somewhere. So we implement the return value, it receives the value, and then we store that inside an optional. So we can later have access to it. So we store it inside the promise object. And then we want that the coroutine starts as suspended. So we return suspend always from initial suspend. We will look at the return types in general in more detail later on. And then we also want to have it suspended in final suspend. So we want it suspended initially, which because it allows us to have a coroutine when we start it. It doesn't do anything, which means we can easily then chain any continuations on it and so on. And we want to have it suspended after the return statement, because otherwise the coroutine would clean itself up. But we want the task object to clean the coroutine up. This is, in general, almost always a good idea to use suspend always here. The other C++ coroutine talks go into that into a bit more detail, but I'm just going to use suspend always here and leave it at that. With that, we can finally understand what the compiler is doing when it sees a coroutine. So here we're having my coroutine returns the task of int. Looks like so, and what the compiler is doing, it first constructs the promise object. It then returns getReturnObject from that promise object. So this will then return a task. And because we are initially suspended, it will immediately suspend. So when we call the coroutine, nothing happens, but we get a task object back, and the coroutine is now suspended. The put statement is left as is, and then the coreturn is translated into promise.return back. Finally, because we're using suspend always in the final suspend, we're also suspending here. So we're suspending here and also preventing a cleanup of the coroutine. Last piece of the puzzle is the user interface for the task, which is very straightforward. Resume simply calls co-resume, and result reaches into the promise and gets the result back. And with that, we can call the coroutine, get a task object, and get the result. Now, what is this going to print? Think about it for a bit. So we're calling the coroutine. It's initially suspended because we're using suspend always, so this doesn't do anything. So this is going to print -1 because result hasn't been computed yet. To actually have it start executing, we need to call resume on the task. When we call resume on the task, the coroutine now at this point actually starts executing, so it will print my coroutine, compute the result. And so now when we query it, we get the 42 back. Now what happens when we call resume twice? Well, the first resume moves past the initial suspend, we're printing, we're setting the value, and then the coroutine is suspended at the final suspension point. When we're calling resume again, the coroutine is now going to clean itself up, but the task destructor is also going to clean the coroutine up. So we're having a segmentation fault because the coroutine is destroyed twice. It's still C++ after all. Now, of course, this example was a bit silly because it's a coroutine, but we don't really make use of the coroutine effect. So let's actually suspend a coroutine, and this pseudocode continue return can be spelled as co-await std suspend always. So here we're adding co-await suspend always inside the coroutine. Then we're printing something after the suspension point, and then we're returning 42. And now we actually have to call resume twice. The first resume moves it past the initial suspension point, so we're printing the my coroutine, and then we're suspending again. And then the second resume continues after the second suspension point, then we're printing after suspend and returning 42. And this can then be received here because it's stored in the promise object of the task. We will later look in more detail at what this co-await actually does, but for now, co-await suspend always just means suspend the current code. And with that, we've got all the necessary pieces to actually implement the patrol function as the C++ coroutine. It looks almost the same as the pseudocode, and just instead of continue return, we're having co-await suspend always. So actually proper syntax to suspend a coroutine. And instead of returning void, we have to use task void because we need something that gives us a promise type. Now this is a C++ coroutine. It starts executing, it will then suspend, and when it's resumed, it will update the position once, then suspend again, and so on. So exactly the same as in the multi-threading example, this looks exactly the same. And again, the actual calling looks exactly the same as the state machine. We're getting the patrol function, which gives us a task. We need to resume it once because it starts as suspended. So actually do the initialization, we need to resume it once. And then in a loop after the sleep, we're just resuming it repeatedly. Any questions so far? That does not appear to be the case, so let's continue. Let's look at the same example in Rust. So exactly the same examples, just implement them in Rust. In Rust, coroutines are functions marked with async. So a regular function in Rust is just written with fn, and a coroutine is an async event. The coroutine state machine in C++, it was controlled by a promise. In Rust, you don't have control. It's entirely compiler generated automatically, but you can also write it completely from scratch. So you don't have this middle ground of a bit of customization. You can either do it completely by hand or have it completely compiler generated. There is also not a single coroutine handle type. Instead, a coroutine handle is something that implements the future trait. This is sort of like a Rust version of concepts or interfaces. So this is the same coroutine written in Rust. It's marked with async because it's a coroutine. It returns i32. We are printing, we're inside the coroutine, and then we're returning 42. Because Rust has implicit return, we don't need to write return here. It's just when we have an expression at the end of a function, that is returned. As we see, unlike C++, whether or not something is a coroutine, it can be visible in the interface because we're having the special async marker here. So just by looking at the signature, we can tell, this is a coroutine. And we can also see that we're returning an int and we're saying we're returning an int. So this matches. But when we actually call my coroutine, we're not getting an int back. So it's a different mismatch here. When we call it, we're not getting an int, but something else. But inside the function, we return an int and we say we return an int. To understand coroutines in Rust, we need to understand the future trait. So let's look at that. We're first having this poll type. This is a variant. Rust has built-in support for variants or enums with state. So the poll can either be ready, in which case it stores an arbitrary t, or it can be pending, in which case it stores nothing. Then we say the future trait, this can be, or interface can be implemented for types. We need to specify the output type of the coroutine. So what is the type that is returned when we're done with the coroutine? In our example, this is i32, because that's the value that we're returning. And then instead of providing a separate done and resume, we're having it in one call called poll. Poll takes the future type and either returns pending when it's not ready yet, or it returns ready when it is ready. So this is a combined done and resume, right? When we call it and it's not ready, it is advanced, and yeah. Three things to point out here. The first thing here is this use of pin. This is some technical details. We get back to that later, but it just ensures that we can't move future type around while it is being polled. This would cause issues with self-referential pointers. So that's what pin means. Then we're having this context parameter here. This is not too important right now. We look at that later on. And this syntax here just means that the context takes an anonymous lifetime. It's not too important. It's a Rust thing. The compiler will remind you if you forget. So the compiler transformation in Rust is a bit different. What the compiler is doing when it sees this function is it first generates a type. It will then implement the future trait for that type, and it will then create a function that creates a new object of the type. So this is the type, my coroutine future, and this is also the place where it will store all necessary local variables of the coroutine. Then implements the future trait for that type. So in our case, the output is I32, and the poll function is very straightforward because we're not having any suspension inside our coroutine. We're simply printing, hey, my coroutine, and saying we're ready and return 42. And then the compiler has transformed the async fn my coroutine into a regular function my coroutine that instead of getting us an int back, it gets my coroutine future. So it constructs my coroutine future. This can then be polled to actually start executing the coroutine. So when we call the coroutine, just like in our C++ example, nothing happens because it just constructs an empty future that hasn't been, right? To actually advance it, we need to poll it. Calling poll is a bit tricky because we need to first of all pin it and also provide a context. So I've just hidden that away into the function resume, but this just calls poll and translates the output into an optional. So we can call resume on our future. This will now start executing. It will print my coroutine and return 42, and then we can print the result back. And unlike in C++, if we try to resume it again, we will get essentially a panic or a termination instead of a segmentation fault because we can't resume it after it's already done. Again, this example was silly, so we also need a way to suspend a coroutine, and this is exploiter code continue return in Rust can be spelled suspend always.await. We will again look at it in more detail later on. But for now, we can just add a suspension point here, suspend always.await. Then we are after the suspension point, and then we return 42. And just like in the C++ example, we now need to call resume twice. Then we get the final value back. Suspend always isn't part of the standard library. Instead, I had to write one myself. Let's look at that. So for that, we need to implement the future trait for some type. So this type is suspend always. It needs to store state. We need to remember whether we're in the first or second invocation. And then the poll function simply says if we're in the first invocation, we're suspending, so return poll pending. Otherwise, we're ready. And this empty tuple here is essentially the equivalent of void. Then the function suspend always just gives us an empty future where we're initially first. So this is incomplete. We will look at that later on. But for now, it's enough to understand that when we see this function with the suspend always.await, the compiler will generate a future trait for my coroutine. Its poll function will first poll our coroutine, and then when it reaches the suspend always, it will forward to the inner future and poll that, and then it's done. So when we resume it, we're first polling the outer one, advancing it, and then here we're resuming and polling the inner. And again, with that, we can also implement the guard part for the Rust coroutine. So in C++, we were passing a simple reference here. Rust doesn't like them, so we have to use a cell. Details are not too important, but it's just otherwise a direct translation of the syntax. It's an async function because it's a coroutine. We're initializing it, we're having the loop, we're suspending at this point, and so on. And in the main function, we are creating a new cell, we're calling petrol, then we're resuming it because just like in C++, it starts out initially suspended. More precisely, petrol only constructs the future and it doesn't do anything unless we start polling it. And then we're sleeping and resuming it later on. Any questions about this Rust implementation? Okay. Then let's recap what we've seen so far. In C++, a coroutine is an implementation detail. just looking at the signature, we can't tell whether or not something is a coroutine, whereas in Rust, it is visible in the interface due to the async modifier. This is a bit of a different philosophy, but it doesn't really matter because if we want to hide that something is a coroutine, we can write an async function and then provide a wrapper function that calls the async function, and this returns the future, and then we're just having a regular function that returns the future, and we don't know whether it's implemented as a coroutine or by hand. As a consequence, in C++, the written return type matches result from the call. So our coroutine returns task of int, and when we call it, we get task of int. But it does not match the returned expression. We're returning an int, but the return type is task of int. In Rust, this is the other way around. So we're saying it's a coroutine, an async function that returns an i32, and we're returning an i32, but this is not actually the type that we get back when we call it. In C++, there was this compiler-generated state machine, and we could customize it using the promise type. Whereas in Rust, we can't customize the state machine. If we want to customize it, we have to write it completely by hand. It is not possible to write a coroutine state machine by hand in C++. In C++, we had a single type, a coroutine handle that can only be used with coroutines. Right? So if we want to have our own state machine, it can't be used with coroutine handle because it isn't a coroutine. In Rust, the coroutine handle is the type that implements future. And this can be implemented ourselves, as we've seen, so we can use it for our own state machines. And again, this sort of different C++ is already a more low-level, more powerful thing, because using the promise type customization, we can do all kinds of things. For example, we can completely overload return inside the coroutine. Using the return a value function, it can do whatever we want, right? It doesn't need to actually store the value, it can just print it. Right? So we can have co-return foo mean print foo if we want to. And we can also use it to do non-coroutine things, like people have written optional chaining and so on using Rust has the question mark operator for that. C++ can use co-wait because it's just a silly thing that we can do. Whereas Rust has a more high level and more strict approach here. But the real differences start now when we actually look at awaitables and resumers, which are also the more interesting parts of a coroutine. So in C++, an awaitable is something that overloads operator co-await. And the awaitable is also the resumer. So when we await something inside the coroutine is suspended and then later resumed when the result is ready that we're waiting for. And the thing that resumes it is also the awaitable. So the awaitable is also responsible for resuming the coroutine. As we see in Rust, this is not going to be the case. So an awaitable is just a type that overloads operator co-await. This is in fact optional. An awaitable can also be an awaiter itself. So we don't need to provide an operator co-await. We can also turn an awaitable into an await. To understand that, let's look at the simple example here. So we're printing, we are before the await, then we are awaiting something, getting a value back, and then we're printing after the await. What does the compiler do with that? This can be customized again using the awaiter interface and the three functions await ready, await suspend, and await resume. And what the compiler is doing is essentially this. So the first thing it does, it calls awaitable operator co-await, which gets us the awaiter back. This awaiter is then stored inside the coroutine and becomes part of the coroutine state. As we'll see, that is really useful. Then as an optimization, it asks the awaiter, hey, are you already ready? Because if it is already ready, no need to suspend anything, right? Just continue on as is. If it isn't ready, it calls await suspend and passes it the handle of the current coroutine is inside. This is really powerful because it means await suspend receives a handle for the coroutine that is waiting on the result. This is also necessary because await suspend then needs to store that coroutine handle somewhere and ensure that the coroutine is resumed when it's ready, because it's the responsible of the awaitable to resume the coroutine. After we did call await suspend, we suspend ourselves and return back to the caller or whoever called resume last. This is also important because we know when we call await suspend, the coroutine is essentially already suspended, so we don't even have any race conditions to deal with here if we introduce multiply. Finally, eventually somebody will resume the coroutine, or more precisely the awaitable will resume the coroutine, which means we end up here. We're calling await resume, and this will give us the value back of the co-await expression. We can then use it and continue on with the execution until the next suspension point. We've already seen an awaitable suspend always. This is a very trivial awaitable. It's never ready because we always want to suspend. Await suspend and await resume does nothing. In most examples, await ready always returns false, and await resume does nothing, so we'll mostly omit those functions. And the interesting part is await suspend. The functions initial suspend and final suspend from the promise do in fact return awaitables. So the actual translation is as follows: we construct a promise, and then we co-await promise.initial suspend. In our case, in the case of suspend always, this always suspends. So this is the equivalent to just suspend at this point. And when the coroutine is done, we co-await promise.final suspend. So in C++, it is the responsible of await suspend to schedule the coroutine for resumption, right? Because we are awaiting something called await suspend. We give us our coroutine handle and want to say, hey, when you're done, please resume me so I can continue work. This means that our actual implementation of the petrol function was a bit bad because we're using co-await suspend always. And as we saw, suspend always, its await suspend function does nothing. This is because suspend always is merely designed as sort of a marker type for initial suspend and final suspend to indicate that it should always suspend. So using this, we're not right. We don't fulfill this responsibility because suspend always doesn't resume the coroutine. Instead, we manually had to resume our coroutine in the main loop. So let's fix that by writing our own awaitable that also then later resumes the coroutine as necessary. This awaitable is a timer. So it's an awaitable because it provides operator co-await. And when we await it, this will suspend the coroutine and have it resumed on the next tick. Then the next tick is reached when we call tick. And this simply iterates over all coroutine that are currently waiting on the timer and will resume them. We're going to use it like so. So our petrol function takes the timer. And then instead of awaiting suspend always, we are awaiting the timer. And then after the sleep, we call timer.tick. This will then go ahead and actually start executing, resuming all coroutines that are waiting on the timer. Of course, when we call it, coroutine starts to suspend it. So we actually need to resume it once to reach this point. Otherwise, it will never call co-await on the timer. For that, I've renamed resume from the task to start. So we start the coroutine, it now starts executing. It will await the timer, and when we call tick, the coroutine will be resumed and continues on. If we want to add another guard, we simply call petrol again and also call start on that task. It will also register itself on the timer and also be resumed here. So I want to point out that this tick call then means it is potentially expensive because it actually starts executing coroutines on this thread, right? Okay, let's implement the timer. And for that, let's realize the inside again that the awaiter is stored as part of the coroutine. So when we call operator co-await, we get an awaiter object, and this object is then stored on the coroutine. So we can use it to add additional data onto the coroutine. This means we can easily implement the list of coroutines currently waiting on it using an intuitively linked list without any dynamic memory allocation, because we can have the awaiter sort of inject the next pointer into each coroutine. So the timer simply needs to remember a pointer to the first awaiter, and then each awaiter remembers the coroutine that is currently waiting on, and a pointer to the next awaiter. Await ready and await resume, as I've told you, is uninteresting. Await suspend is where the real magic happens, and it simply takes a handle for the coroutine that is waiting on the timer and remembers it, and then adds it to the linked list. Then the tick function goes ahead and iterates over the linked list and calls resume on all coroutines that are waiting on it. It's a bit, this exchange here is really important because when we call resume, we execute arbitrary code. In particular, in our example, we execute a coroutine that will immediately go ahead and register itself again onto the same linked list. So we need to first set the linked list to empty before we start iterating. Otherwise, when we call resume, the coroutine just adds it back to the linked list and we're having an infinite loop here. And with that, let's walk through what's actually going on here now. So we're calling start on the task object. This will start executing the petrol. It reaches co-await timer and says and adds itself to the linked list of coroutines currently waiting. Then inside the loop, we're calling timer.tick. This iterates over the list, calls resume on the coroutine, which then loops around and adds it back self onto the list, and so on, and so on, and so it just works. Now, it's a lot more code than we had before. We need to write all this timer, and we have this bit of a tricky like linked list stuff. So you might ask yourself, well, what's the point, right? It worked before with the suspend always, so why go to all this trouble? And the answer is it's sort of necessary to go through all that because what we are about to do now. We want to factor our coroutine out into two separate coroutines that we call. So we have this function move that simply advances the position steps times, waiting the timer to synchronize the time as necessary. And then we want to call it from another coroutine. Of course, this doesn't work because calling coroutine does nothing, right? Due to the initial suspend. So what we actually want to do is we want to call the coroutine and start executing it. But then when the coroutine suspends here, we want to have it on resumption, continue here, but then eventually jump back here, right? Because we want to call move, have it be executed, don't care that it is suspends, but eventually reach back. So what we essentially want is the semantics of the regular function call, just that the function that we're calling can suspend itself, but can also suspend us recursively. To do that, we need to use co-await and turn the task object into an awaitable. So the idea is we're calling co-await. This will then register the petrol coroutine with the move coroutine. So the move knows that when we're done, we want to go back to petrol, right? Just like in a regular call stack. If move is then suspended in between, this doesn't matter because it knows that once it reaches the end, we want to continue with petrol. So for that, we need to remember a continuation inside the promise type of our task. So just remember store a coroutine handle in there and then change final suspend because this is called when we reach the very end of a coroutine. And we can use the await suspend function to have it say at this point, if we have a continuation, resume the continuation. So when we reach the end of the coroutine, we can resume a continuation if we have. And the way this works is await suspend receives the coroutine that is waiting on this awaiter. But because final suspend, it is always our coroutine, in fact, getting a coroutine handle to ourselves back. So we can get the promise, right, which is our promise, and read the continuation. The second piece of the puzzle is the operator co-wait of the task. So for that, we simply need to return an awaiter. And again, the interesting part is the wait suspend function. It receives the coroutine that is waiting on the result of the task, which means this is our continuation, right? When we're done with the coroutine that we are waiting on, we want to continue with the coroutine that is awaiting us. This isn't enough because this then wouldn't do anything, right? It will just suspend the parent coroutine and then return to its caller. So instead, we immediately then start executing the inner coroutine by calling handle resume. Okay, so this is a lot of subtle things. So let's just walk through the example. At some point, we are resuming execution of petrol. This will then call move. This does nothing, it just gives us a task back. We're then calling co-await on the task object for move, which will suspend petrol because this is what co-await does. It calls await suspend, which sets the continuation of the move coroutine to the petrol coroutine. So we know that when move finishes, we want to continue with petrol. And then it actually starts executing move. So at this point, we start executing the move coroutine. Eventually, the move coroutine will call co-await on the timer, which again suspends the move coroutine. And then as we saw, it registered that the move coroutine is continued on tick. So when we call timer.tick, we will continue with move. So we call timer.tick, it resumes move, which then finishes. At this point, we're calling final suspend, and its await suspend function reaches back to the continuation and continues it, which means we now continue on petrol from this point, and the loop continues. And this is also where the co-await suspend always breaks. Because if we use co-await suspend always inside move, nothing happens, right? Instead, we're having all the way at the back, we're calling resume, but on the wrong task. It calls resume on the petrol task, but you don't want to execute it, we want to execute it and move. So we somehow, if we were to use co-await suspend always, need some way to transfer this task object from the inner coroutine all the way back to the caller. And this isn't done nicely, right? You can put it in a global variable or something, but there isn't really a nice way to do. So instead, we have to use this interaction over the timer, which keeps track of, hey, what is the innermost coroutine that is actually waiting on us? And it will then resume that. And this will then propagate all the way back due to the continuations all the way back to the parent. Okay, so let's try it out with many nested calls. We're having a child coroutine that does nothing. It immediately returns. And then we're having a parent coroutine that just awaits it many times in a loop. And what we expect to do is like we're calling corob many times in a loop, right? And as we can see, the segmentation parts. So what is actually going on here? Well, let's look at the call stack. We're calling resume on coroutine A at some point. This then calls await suspend on the awaiter for coroutine B. This calls resume on coroutine B because this is what await suspend does. When we await a task, we start executing that task. The coroutine B finishes, so it calls resume on coroutine A because that is its continuation. Coroutine A is now in the next loop iteration, calls await suspend on coroutine B, which calls resume on coroutine B, which finishes, which calls resume on coroutine A, which is now in the next loop iteration, and so on. And we are having a stack overflow. Because we're calling and calling and calling and calling, right? We keep calling resume over and over again. To fix that, we need to use tail calls. So tail calls are a way to call a function without actually pushing anything onto the call stack. Instead, just like a loop, the compiler, the processor simply jumps to the first address. And to use tail calls, instead of calling handle.resume, because this is a regular call, we can instead return handle. And when we return a coroutine handle from await suspend, this tells the compiler, hey, I know what to continue with this particular coroutine, so please call resume for me. But the compiler can do it in such a way that it doesn't involve a call, right? So it's a tail call. It's a bit more tricky for await suspend. Because we only want to call resume if we actually have a continuation. So in the other case, we have to return no up coroutine, which just indicates, hey, I don't have a continuation. So instead of continuing with another coroutine, just continue back with our last call. And now this would actually work, right? We can call it many times in a loop because we're not having any call stack issues. This will just work as it's. Currently on GCC, you need to turn optimizations on for it to actually work, but this is a bug in the implementation that will probably be fixed at some point. Any questions about awaitables in C++? Okay, this was the more difficult part. Let's look at awaitables in resume in Rust. And they are a lot simpler there because awaitables are futures. In C++, we had this difference between coroutines, controlled by the promise, and awaitables, which are things that coroutine can wait on. In Rust, we have futures, and futures can be awaited, and only futures can be awaited. So there's just a single concept. In contrast, in C++, we had the resumer, which was also the awaitable. So when we await something, it also needs to resume us. In Rust, this isn't the case. In Rust, instead, you need to write some user-written executor. So you need to have some sort of global list of coroutine futures, and then you need to have something that repeatedly polls them as they can make progress. Now the question is, of course, how does the executor know that it should poll a future again, right? It can just go ahead and poll everything whenever, but this wouldn't be ideal because the coroutines might not be ready to make progress yet, right? So the executor, someone needs to be informed that the future can be polled again. And this is where the context comes in. The context, all it does, it provides a waker, which is an object which provides a wake function. And when we call it, this informs the executor, hey, this future is now ready to be polled again, please poll it again. So we can imagine, for example, like a thread pool, it has a list of all futures. And whenever a wake is called by a future, it will then put that future and put it on a work list for a particular thread. The thread will then go ahead, call poll on that future, and then put it back onto the global list of futures. So the correct implementation of suspend always needs to account for that. So whenever we return poll pending from a function, we need to ensure that we're calling wake when the future is ready to be polled again. In the case of suspend always, we just want to temporarily suspend it, right? So it can be immediately polled again. We don't need to wait for anything. We just want it to have suspended. So we can just call wake immediately here. And then we return poll pending. But for more complex stuff, we might need to put that waker somewhere to ensure that it is called when we're ready to make progress. With that, we can now also look at the implementation of the resume function. So all we need to do is construct the context from a waker, and because to fit all the code on the slide, our executor is really dumb. We're just manually calling poll on a future. So we don't need to actually do anything on wake. So we're just constructing a node waker, get a context back, and call poll. We also need to pin it, Rust specific things, touch on that a bit more later, and then translate the result. Then we can call a coroutine, and this resume function is now an executor. And as I've said again, a real executor would have like a list of all futures, so we would register that future in that list, and when we call wake, it will be moved onto a list of futures that are ready to be polled, and then and so on. But for simplicity, we're just manually polling a future ourselves and completely ignoring wake. Because of the way this works in Rust, our code was already fine. In C++, using co-awaits is meant always, and then calling resume manually isn't a good idea, but in Rust, it's perfectly fine. It just works because we're meant to do it that way. However, nonetheless, just to see a contrast, let's also implement the timer in Rust to see how it works. And because Rust doesn't have the awaitable objects where we can sneakily inject state into the coroutine, we're just having a timer that can be only one coroutine can wait on the timer at a time. That way we don't need to worry about any like container things. So this is our timer. It remembers the current time and also the waker. Because the timer, it again has a tick function, but the tick function can't execute the coroutine, can't poll the future again, because this isn't its job. The executor is meant to poll it. Instead, the tick function, all it does, it calls wake. It informs the executor, okay, we're now at the next tick, you can call a poll again. So this is what you're storing here, the waker. Then we're having the block function. This is the equivalent to the operator co-await, but instead of returning an awaiter, we return a future, because future are things that we await. So the usage looks otherwise similar to C++. We are passing the timer. We need to use this ref cell business because Rust doesn't like references that much. Then we are blocking on the timer inside our petrol function, which suspends it. But this time it is not registered for execution because this isn't the job of the timer. It's not an executor. Instead, when we call tick, this simply informs the executor, hey, this coroutine can now be polled again, but then we actually need to poll it again, right? And again, this is a bit silly now because we know, right, we don't actually need to call tick because we can just poll it directly. But again, a real example, we would have this list of futures, and when we call a tick, the future will be moved to the separate list of futures that can be polled, and then they will be put. We also need to resume it once because again, it starts out initially suspended. To actually implement the timer, now the block function, we need to provide a future. So the timer future remembers the time where it was started and a reference to the timer. We again having some lifetime business, it's not too important. And then the poll function does the actual magic when we are still at the same time as we initially started, right? We haven't called tick yet, so we're not ready to be executed, which means we need to return poll pending and arrange that the waker is called. This is done by storing the waker inside the time. So when we call timer.tick, the waker is set and it will be woken up. The executor then goes ahead and polls the future again. And at this point, we can return poll ready. What's left is the tick function. It's very straightforward. We're simply advancing the current time. And if we have a coroutine that is blocking on it, we call wake. Again, this informs the executor. The executor then goes ahead and polls it again, and we're ready to make progress. In our example, we don't have an executor, so we're polling it again anyways. This is fine, just less efficient, but a correct executor would use the wake here. The good news is that because futures can be awaited, chaining coroutines is free and we don't need to do anything. We can just write another coroutine and call await on it. And the way this works is, because you might be asking yourself, why does this work now? Whereas it didn't work in C++, where we had the top level resume. Why does this work here? Well, in C++, we called resume on the task, and this would only resume the top level coroutine. But in Rust, we're calling poll, and the future returned by here, by the petrol coroutine, which will, at this point, then call poll and the move future. So it's sort of like from the top down, we repeatedly call poll. This is why it works. So again, let's compare the two approaches regarding awaitables. In C++, an awaitable is a user-defined type that provides an operator co-await, whereas in Rust, an awaitable is a type implementing future. So coroutines are futures, awaitables are futures. There's just this future concept and nothing else. Await suspend, or the awaitable in general, is responsible for actually resuming the coroutine. So when we call await suspend, we give it the coroutine that is currently waiting, and then await suspend needs to ensure that at some later point, the coroutine is being resumed. this happens from the bottom up. So we have a coroutine that awaits another coroutine, that awaits another coroutine, that awaits an awaitable. The awaitable will resume the innermost coroutine, which is then responsible for resuming its parent, which is responsible for its parent, which is responsible for its parent. If we try to resume only the top level coroutine, as we did originally, this would break because it will only advance the top coroutine. It doesn't know about the chaining. In Rust, this isn't the case. We have the executor that pulls futures, and the chaining happens from the top down, because when we pull a coroutine, it pulls the coroutine it's currently being executed, it pulls its child, and so on. So the chaining happens from the top down, which means we have a top down, we call it pull from the top, executes all the way down. This then, of course, means that coroutine chaining is part of the language. So when we actually go ahead and translate the coroutine into the state machine, the compiler ensures that it calls pull on the innermost future as necessary. Whereas in C++ coroutine chaining requires library code, we need to implement co-await, we need to add a continuation to each task and ensure that it is continued edit. In C++, you can customize what happens when a coroutine is resumed after a suspension point. You can do that in Rust. If you want to do it in Rust, you have to write the entire state machine, which works. It's just more work, potentially. Because in C++, the awaitable is responsible for resuming a coroutine is only resumed when it can definitely make progress, right? Because the awaitable knows when it's ready, and it knows what coroutine it should resume. So when it's ready, it can just resume that coroutine. In Rust, the executor just keeps pulling futures as often as it wants, right? Our dummy executor just pulls the future and pulls the future, right? Even though it might not make progress. So as an optimization, there's this waker. The coroutine can inform the executor, hey, I'm now ready to be pulled again. And a smart executor would only pull coroutines that are actually ready to make progress. Due to the way this works, there are also slight differences in common operations. For example, we might want to execute a coroutine on the thread pool. In C++, it can be done in this elegant way by providing a schedule function to the schedule, which returns an awaitable. And when a coroutine calls co-await on that, what happens is the coroutine is suspended. It passes its coroutine handle to await suspend of the thread pool's awaitable, which can then put that coroutine handle and assign it a thread in the worker list of a thread. So when the thread goes around and resumes it, the coroutine is now suddenly on the thread pool. So co-await can transfer execution from one thread to the other. In Rust, this isn't possible. Instead, when we call my coroutine, we get a future. And because this future will recursively pull itself again, what we need to do is pass that future to the thread pool, which will then put it onto a list. So in the Rust case, the thread pool, each worker has a list of futures. And when the wakers are ready, the thread will go ahead and pull those futures. Whereas in C++, the thread pool has a list of awaitables that are ready to be made progress. Of course, you can also provide the same interface in C++ by simply having a task up, right? By simply wrapping, calling a coroutine, which gives us a task back, and then we're calling co-await, creating a new coroutine that co-awaits the task and transfer it that way, because we just need to get the handle. And we can also implement the C++ way in Rust. It's just by default, it's sort of different philosophy there. Finally, let's look at the obligatory socket example. We want to read from a socket inside a coroutine. So we use co-await or .await and see how that works. Rust, again, is a bit simpler. So we need to implement the future trait for type. The output is like a vector of bytes that we thread. And then we're checking, in poll, we're checking, do we have data to read? If so, we immediately return that data. Otherwise, we return pending and need to arrange that we call wake. We're ready to make progress when data is received. So let's assume that the socket has like an onData function that we can give it a callback, and it will then call wake when it receives data. So internally, there's some kernel interrupt. When the socket has data, we can call it executes. It then calls wake, which informs the executor, hey, this code future can now be pulled again, and advance it and get the data back. In C++, we don't write a future, we write an awaitable. Here we can actually now use all three functions. So we're ready whenever we already have data. If we have data, we don't need to suspend. If we do suspend, we get the handle to the coroutine. We need to ensure that the coroutine is resumed. So we say that when we receive data, we resume that coroutine. And when it is resumed, return the actual data. Now, this isn't quite ideal, because on data is the callback here, this lambda is called by some interrupt routine or something. And when we then call waiting.resume, this executes arbitrary code of the coroutine, and this can do whatever we want, right? It can do IO, it can do block, it can do memory allocation. So this isn't ideal to be called in interrupt. So the correct approach actually would be to just copy Rust approach, and instead of actually resuming the coroutine immediately, instead add a waker API and inform somebody else, hey, potentially a different thread, hey, please resume the coroutine now. So we're having a thread pool for IO threads, and when we call on data, we want to resume that. So this can look like so. So on data, we are getting some sort of context back from the socket and say, hey, you can now resume this coroutine handle. And this will then put it on a list of thread pool, and when the threads get around, they resume the coroutine. Right? So in C++, we can easily copy Rust approach, but I don't think we can easily copy C++ approach in Rust, because we always have to go through the back. Now, finally, let's look at coroutine allocation, because this is another of the big differences between Rust and C++. The issue is that coroutines need to store state. So in our case, we're having function myCoroutine. It reads a string, it then suspends itself and then prints the string, which means the string needs to persist between the suspension point. So it needs to be stored somewhere. And we can't just put it on the regular call stack like any local variables, because we might have many coroutines currently being in flight in various stages of execution. So we can't just use a stack for that. We have some sort of call tree. One easy fix for that is so-called stackful coroutines, where each coroutine uses a separate stack. So when we call a coroutine, we allocate a new call stack for that coroutine, and the coroutine will then use that call stack to store everything it pleases. Of course, the issue is how big should we make that call stack, right? And if we make it too small, we might have a stack overflow. If we make it too big, we might waste space. So this makes coroutines a lot more resource intensive, because we need to preemptively allocate big chunks of dynamic memory or something. One big advantage of this approach is when we have a regular function that just calls a function pointer, we can pass it a coroutine. This works fine, even though the coroutine then later suspends itself, because the regular function doesn't need to worry about it. Suspension simply returns from the coroutine call stack, and this is completely transparent to any functions in between. This is one big advantage of stackful coroutines, because we can just pass coroutines through regular code. In both Rust and C++, where we don't have those, when we want to pass a coroutine to regular code, we need to copy that function and call it with co-await or .await. Right? We have this duplication between regular APIs and coroutine APIs, which is an idea. But for more high-level language, for example, Go's coroutines are implemented like that. Each coroutine has a separate stack, and we can just immediately suspend in there, and so on. Rust does something really intuitive, because Rust already has a type, right? It needs to generate a future type for the coroutine, so just put all the data in there. So this is the current state of the state machine, any local variables that need to persist, and so on. This type is necessary anyway, because, like I said, we need to implement future on that, so we can just put all the data in there and then return it from the function and so on. This is also the case where pinning is important. For example, we could imagine that bar is actually a pointer to foo, right? So we have a local variable in a function which stores the address of another local variable function. But because this is in a type, the type can move around, which will then change the address of the self-referential pointer. And because Rust doesn't have move constructors, there's no way for us to patch up any addresses when the future is removed. So we have to pin it, which ensures that it can't move in memory. Right? Once we actually start pulling it, it has to be pinned to ensure that any pointers that are set to other local variables stay set to those variables, and it doesn't move around in memory. C++ does something different. C++ heap allocates coroutine state. So it heap allocates the POM subject, any parameters of the coroutine, the current suspension point or the state machine state, so the state of the state machine, and any local variables that need to persist between suspensions. And coroutine handle is a typeized pointer to that state. So it's just a pointer to the state, and then when we call resume, it just reads the current suspension point and gets a function point and so on, does its thing. This has the big advantage that we don't need to worry about pinning, because once we heap allocate the state, it doesn't move, right? The coroutine handle can be moved around, but it's just a pointer, so it doesn't matter. But this is still a bit of an unusual design decision on C++ end, because it does implicit and automatic dynamic memory allocation every time you call a coroutine, right? This doesn't really fit with C++'s philosophy. So why is that the case? Well, the Rust case isn't that ideal either. It's a trade-off. In Rust, the coroutine state is part of the type system, right? We have this future type and that implements the future trait, and this is part of the type system. This means that you as a programmer can use various metaprogramming tricks to figure out what exactly is the type of my future. The upside is you can put the coroutine state like any other variable, put it on the stack, return it from functions, move it around, unless you've actually started following it, in which case it is pinned, and so on. Whereas in C++, the coroutine state is completely type erased. You have no idea what this type is. So you cannot figure it out using decal type. There's no way to like dereference a coroutine handle and get the state back, right? All you have is this coroutine handle type. Of course, this means that as it's type erased, it needs to be heap allocated, because type erasure requires heap allocation as you don't know this size. However, in Rust, the type is known, so also the size of this type is known at compile time, which means that when we do front-end stuff like getting the type of the size, the compiler already needs to know the exact type of the coroutine future. This means that the coroutine future has to be built before any optimizations can happen, and it is also part of the AVI. This means that the coroutine state is potentially bigger than necessary, because it might need to store all local variables that could potentially live beyond suspension, even though a later optimization pass would move them out, right? The coroutine state has to be more conservative, bigger than necessary. In C++, this isn't the case, as you cannot query the size at compile time. The compiler frontend doesn't need to compute the size, only the backend. So this can be done after optimizations. It is not part of the API. It is a type-erased thing, and it's only as big as necessary. But of course, the trade-off has to be dynamically allocated. Although this isn't entirely true, so C++ has something called Halo, the heap allocation and vision optimization. When we call a coroutine, as I said, we need to allocate the coroutine state. This is essentially new. And then the destructor of the task calls destroy, which deallocates the coroutine state, which is a delete. So having a new here and a delete here. And in the simple case where the task doesn't return from the function, the compiler can easily lift that into a stack allocation. So instead of using a heap allocation, we use a stack allocation constructed and they're automatically freed from return from function. So when we have the simple case of just we're calling it coroutine, we're advancing it, but we never return the task object from the function, usually it can be addition. A common case where this happens is when we call correlate inside the coroutine for another task, as we've seen with our move function. Then we're just getting a task object, we're executing it, and then we're returning it. So this is where the optimization can take place. So usually you're only paying for the very first heap allocation when you initially start executing a coroutine, and everything else is free. But of course, this is an optimization. This isn't mandatory. With that, we are at the end of my talk. So let's recap really quickly. Coroutines are functions that have the additional ability to be suspended and later resolved. In C++, so the compiler has to implement that by generating a state machine. In C++, you have some control of the state machine using the promise type, and you have the concept of awaitables, which is something that can be awaited, and they then take care of resumption. Rust allows you to write the entire state machine by hand, right? You can't customize it, but instead you can write it entirely yourself. And you don't have the concept of awaitables. Instead, only other coroutines can be awaited. And resumption happens by a top-level executor from the bottom up, from the top down. This is ensured by having the breakers, which inform the executor when a future can be polled again, so they can smartly poll them. Whereas in C++, the awaitables resume the coroutine, the innermost coroutine that's waiting from it, and execution happens from the bottom up. As we saw with the allocation, there's a big trade-off between typed versus type-erased coroutine state. Advantage of typed coroutine state is that we don't need dynamic memory allocation, but it might be bigger and you have to worry about pinning. Whereas in C++ with a type-erased coroutine state, we require heap allocation unless it can be optimized away, but the coroutine state can only be as big as necessary and we don't need to worry about pinning. If you later go to that URL, you will find necessary information, additional information about coroutines. I will also share the slides there in addition to uploading them. If you follow me on Twitter, I will tweet that link out. And if you like this talk, consider supporting me. Thank you. If there are any questions now, feel free to ask them. Otherwise, I will also hang out a bit in Gathertown after the talk.